So let me start off by introducing Jordan. Jordan is a technology futurist with AutoDesk, educational and professional background in architecture, aerospace, cloud computing, and composites. He was the founder and CEO of Horizontal Systems, oversaw the creation of Glue, 3D cloud-based collaboration platform, which was acquired by AutoDesk a couple of years ago. Jordan's doctoral dissertation at Harvard developed the concept of distributed manufacturing systems for composites. He has consulted extensively for the United States Air Force Research Laboratory and Office of Naval Research to develop next-generation additive manufacturing technologies. So let me welcome Jordan Brandt.
Thank you, Don. Signore, signori, buongiorno. I'm sure that this morning many of you woke up and thought, I should just stay in bed today. Not because it was raining, but because Team America lost. So I appreciate your persistence and tenacity in getting out of bed. And for a lot of us, the Italians, the Americans, the English, the Brits in the group, Mexico, we're thinking, you know what, it's over. We're not even going to watch it anymore. Because surely there aren't any French or German or Belgian or Dutch fans in the crowd, are there? Oh, a couple. All right. We'll watch it just for you guys. So best of luck. I'll get started here. Is this my button? Awesome. I assume the green button's the go button. All right. So I wanted to start off with a little client project that we had. So these guys, Lightning Motorcycles, they're in the Bay Area, south of San Francisco, and it's a startup, and they're making electric motorcycles. And I have to say this as a proud Ducati owner. These guys beat the pants off of Ducati and every other internal combustion engine motorcycle manufacturer in a race up the top of Pikes Peak, a mountain in the United States recently. So we have to watch out. Electric bikes are not just for putting around town, but they're winning real races. So these guys wanted to make a lighter weight version of the swing arm, which is the thing that holds the rear wheel onto the motorcycle. And being a motorcycle fan and loving making things, we decided to help them out. So I was using our new cloud modeling tool, which also enables the manufacturing in Fusion 360. And so we modeled up this, and the plan was to 3D print the structure, use some aluminum machined components to insert into the structure, and then laminate the entire thing with carbon fiber. And here's actually an image of this thing before it was laminated with carbon. So you've got the 3D print, the machined parts. We learned some things about mating these two kinds of components together and also how to simulate and model these things. But I bring this story up because in order to do the composites fabrication, we had to set up a vacuum chamber so we could bag this and do the layup. And in order to do that, I had to set up the composites facility at our R&D laboratory. And I needed this little component. There's a little brass fitting about this big. So I went to the local hardware store, and this is the hardware store that's been in town for ages, right? And there's that guy who's worked there for 30 years and knows everything in the store. So I said, hey, I need this little fitting with these threads in order to hook up to the vacuum line. He said, okay, let's go downstairs. So we went downstairs, and this is the wall we looked at. All right, there's tens of thousands of these little fittings up there. So we sat there for nearly an hour going through every one to try to find the one that I wanted. This is the one that I wanted. They didn't have it. All right, so these guys stocked all of this inventory, most of which probably hasn't moved in over a year, in the hopes that they might have the one piece that I need when I go in. So out of this, they wasted 45 minutes of an employee's time, wasted 45 minutes of a client's time, and I came out with a very unhappy experience. So how might this entire paradigm shift? All right, let's look at another example, beloved Barbie. Now, before you laugh, Barbie is a $2 billion a year business. I didn't know this before getting into this research. So Barbie is composed of about 200 grams of plastic, and she's typically put in a big box like this, manufactured overseas, packaged up, and shipped around the world. So you can fit about 12,000 Barbie boxes, 12 to 13,000, in a given 20-foot shipping container. If you were to ship the equivalent polymer powder in that shipping container, you could get 250,000 Barbies. into one box. Right? It's kind of a stunning figure if you think about it. So how might that change the paradigm if we could enable localized manufacturing? And we talk about this like it's hypothetical, but this is actually happening now. This leapfrog in manufacturing as we talk about it. And think of this impact on emerging markets, right? So if you're an emerging market and you're looking to invest billions into infrastructure for ports, roads, shipping, freight, or you could invest it in lighter, more agile factories that can actually produce things where it's needed, right? And the analogy is very clear in telecommunications, right? You look to India, you looked at parts of Latin America, you looked at other regions where they didn't have landline infrastructure, and they're skipping over that. Who needs it when you have mobile technologies? Same thing with power generation, right? A lot of emerging markets are looking to distributed power generation because they know what happens when you have big centralized grids. I, for one, lived in New York through a couple of blackouts that took out the entire East Coast. Has anyone else in DC, New York, Boston experienced one of those things? Right? So why not go to a distributed production system? That's exactly what's happening. And what you're seeing on your screen here is actually the network of 3D printers enabled by 3D hubs. So we partnered with these guys who are basically linking everyone who has a 3D printer that has spare capacity in their machine. And to be honest, most machines are only utilized about 5 to 10% of the time, if that. By the way, if anyone wants to sign up, I hear there's a good opportunity in Greenland, Greenfield site. You should go for it. But what's really exciting about this also is not just the efficiency of production, but the fact that now markets that were previously unable to design and make their own stuff can do so. Because you think about it, what have industrialized nations known about the needs in developing worlds? Right? You think about refrigeration engineers in North America or Europe probably don't know much about refrigeration in sub-Saharan Africa. So enable the markets to design and make their own stuff. And that's what these guys are doing. So I thought about it on the flight over. I popped in Milano as a search on 3D hubs and figured to see how much capacity there was. Turns out there's 104 3D printers in this area. And what's great about this, it gives you the rating of all the people with the printers. It tells you the materials they can do. So if I need nylon, ABS, PLA, this guy down here has some elastomeric materials. And it gives the ratings, right? And by the way, I can get one turned around within 2 hours. That's pretty incredible. Also, think about if I wanted to produce a lot of something. Yes, these machines are slow right now, but if I've got 100 spare machines in the local region, I can enable all of them to manufacture. Now, this brings up some critical questions, and getting back to the topic of this committee and this group about standards, the quality control standards. If I have 104 different people printing it, how do I know that every one of them is coming out the way that it should be? Also, what I have redlined here, this STL file format, it's got to go. It's really bad. And we'll get into that in a little bit and what those alternatives might look like. Let's look to some other examples here. A few weeks ago, a gentleman named Francis Battanti, he's a New Yorker, has a studio in Brooklyn, and is designing some components. He's actually into fashion, so I thought this was apt for the Milan environment. And he's now designed a line of products called the Cloud Collection, which is very apropos because the designs are released in the cloud, and he's partnered with 3D hubs to enable them to be printed locally. So you can just go online, have that user experience. That's the equivalent of packaging, right, in the cloud environment. You have the user experience of either configuring your own or finding something that you like and then having it printed locally next to you. No shipping, no packaging, none of that necessary. Now he's working on a new line of products that are actually taking advantage of some of the other capabilities with additive manufacturing, multi-material capabilities. Now, can you guys play, there's a YouTube video here that I think is amazing, showing some of the innards of this design, but he's basically created this using algorithmic methods, right? So the designer of the future is not what we would call explicitly designing stuff. This is too complex for a human to be able to draw out, right? So the days of drawing fillets and bosses and features is over. The designer and manufacturer of tomorrow is going to be teaching the machine how to design and make the thing. So what you're seeing here is a continuous cross-section traversing the thickness of this product. And the different colors represent the different materials. So from rigid to elastomeric, from opaque to transparent, all within the same solid object. So this begs the question now, how do we actually represent this information? How do we develop standards around this information when every single material, every single product is bespoke? Here's a project that we've been working on at AutoDesk with another client in the Bay Area called Moon Express. So Moon Express is a private company. They're sending a lunar lander to the moon next year, 2015. It's going to ride on top of a SpaceX rocket, and it's going to touch down. It's going to be the first time that a private company has put something on the moon. According to some people, it's the first time anything's been on the moon, right, for the conspiracy theorists out there. What's incredible about this, we generated this design for a thruster bracket. So the yellow that you're seeing is the fuselage of the lander. This transparent is the thruster itself. And what you're seeing there is the structure to hold that thruster to the fuselage. And basically, this was generated in a technology called Dreamcatcher that's still in our R&D labs. But we fed it the inputs of the geometry constraints and the loads, and this is what the computer generated after about 10,000 iterations to find what the optimal was. So if you look at how this works, is basically we're using genetic algorithms to search all the possible solution space. Now, this is slowed down, but we can go through one of these about every third of a second. So every second, we pump out 3 iterations, we do the FEA, and feed back the results. We want the lightest weight and the highest stiffness to handle the loads of this, basically 5 degrees of freedom for this thruster. Now, you look at this, it's probably not what an engineer would have come up with. The other challenge is getting the engineers to analyze this thing and really trust the results, right? Fortunately, we're able to print these quite quickly. So these are being sintered out of titanium. So you could actually do physical tests on these within a couple of days. So that if you didn't trust the analysis, break it and go for another one. Now, what's interesting here is also getting back to how do we represent this? How do we represent the geometry? How do we analyze it? We actually spent more compute time in the first iterations of translating between the geometric representation and the analytical representation. So one thing's for certain, that the two have to be mutually inclusive, right? We have to go to a discretized volumetric model that's the same for the analysis as it is for the representation and visualization. Now, these are also some neighbors, and I'm realizing now I have so many California examples. I'm sorry, I'm biased here. There's a lot of cool stuff going on in California if you haven't been there lately. These guys in Lawrence Livermore National Labs have a computational materials group where they're designing new materials. So they start with the functional requirements. What do we need the material to do? And then they design a material to fit those requirements. In this case, what you're looking at is a negative CTE metal. So this metal will shrink when it's heated and grow when it's cooled. Never before in the history of the universe has there been a metal that had these properties. And now they've synthesized this at a very micro scale at the labs. And these are real applications. I mean, this is laboratory work, but it's finding functional applications. You think of the temperature extremes that you see in a rocket. This one is centered, by the way, and is being tested physically. So this stuff is making its way into real production, where we're still faced with a lot of these challenges over how do we represent this information, how do we analyze this information, how do we distribute this information. So one thing that we're seeing happening is the worlds of software, hardware, and material are all conflating. It's very, very difficult to innovate in one area without doing all of them. And it begs a lot of new questions. Where's the IP, right? So we're a software vendor. If we develop software to design a new material and instruct a machine how to assemble that material, where is the IP boundary? Is it in the software? Is it in the output of the machine? Is it in the machine itself? Right? And then how do you define these standards? What I mentioned earlier. When not only every geometry or every product is unique, but every material in the product is unique. That's the paradox of a standard. And how do we manage this exponential complexity? And we'll get into the numbers. These numbers get really big really fast when you look at these volumetric models. So one thing that we've done to address this is say, hey, if we need to innovate in hardware, let's just build hardware. Okay? And with this, and I don't know, some of you may have seen this release, we also are releasing the Spark platform, which is an open 3D printing platform. Now, the hardware is really what we call a demonstrator to test out this concept of the open platform and show to hardware manufacturers what you're capable of doing when you integrate into an open software platform. The analogy that BBC used was the Android for 3D printing, which is quite apt. And obviously, with Android, they also released a phone to show developers what you can do with the hardware and software integrated as one bunch. And this really opens up the ability for the entire industry to advance, because every time you look at new hardware vendors, some of the startups are developing new materials for 3D printing, they're all solving the same problems over and over. Support material, nesting software, material selection, previewing what the final print is going to look like. And so we thought, why not just solve that for everybody so that we can move forward and that these new innovative companies can actually solve new problems instead of coming back to the old ones. So what's interesting when you look at additive is that it's really augmenting what already exists. We heard the example yesterday about the injection molding tooling, increasing the throughput rate of injection molding by 30% by printing it with internal cooling channels. It's a great example. And we often read in the media about the all-in-one machine, right? The machine that's at home and you can print your coffee or you can print your replacement part. And maybe that's true in the consumer space, but in the industrial sector, we learned something from the first industrial revolution, is that there's a place for purpose-built machines, right? A machine to print turbine blades is very different from a machine that's printing, I don't know, rear differentials, all right? And we're going to see more of this popping up. And if you look at where patents have been filed by companies like Apple, just filed a patent late last year to print conductive ink on top of 3D objects. Where might they use that? Maybe for printing components in their phone or connecting components that are placed by robotics in a phone. Lego has also filed a patent to print on top of existing Lego bricks. So they're seeing the writing on the wall that they're not going to hold the edge on manufacturing little plastic bricks. It's going to be more about that entire user experience in the Lego brand. So let's use a quick example here. And before diving into this, I want to talk very quickly about the standards right now used in additive and the file representation. So the current standard is an STL format, which is just the surface representation of the object that you want to make, right? It's a polygonal mesh. It doesn't really have any intelligence about what's inside or outside of that mesh. Now, ISO and ASTM have collaborated and have released a new standard called AMF, which is a file format geometrically represented similarly to AMF, but now it includes things like color, material, and other metadata. So it's more intelligent. I'm going to show you that the problem is of just even thinking about file format is already outmoded. Okay, if we were going to print this phone with little bits of material that are about a micron cubed. So one of these bits of material might be that negative CTE metal from Lawrence Livermore, maybe it's conductive glass, maybe it's copper, maybe it's some material that hasn't even been invented yet, right? So if you're going to stack little blocks of this, a micron cubed, if each bit of material is about 50 kilobytes, something the size of your smartphone would be about 3.5 petabytes, a quadrillion bytes to represent that thing in your pocket, right? That's pretty huge. I heard or read yesterday about, what is a petabyte? Basically, if you listen to an MP3 at 1 megabit per second, it's going to take you 2,000 years to finish that MP3. Now, we can compress this, and we can do a lot of software vendors to make the data size smaller. The point I'm trying to make is the scale is exponentiating. And the traditional models, the traditional mode of thinking that we have in folder structures and hierarchy and a file that contains all this will not exist anymore. What's going to be happening is that we're going to be compiling these products simultaneously with the design. And we're going to go to a model that's more like DNA. You think of it, it's a great analogy that's already been used for a few million years, and it works pretty well. Every one of you is a unique product. The DNA is a blueprint. It doesn't contain every bit of material that's in you, but it gives the instruction of how to make all that material. And that's a model that we're looking at and to drive that analogy. So if we think about a streaming protocol instead of a file format, and HTTPS, of course, it's going to be secure, so that we can actually stream the information from the cloud, from the compute environment directly to the machine and instruct that machine where to place each bit of material or how to formulate each bit of material. Now, that may seem weird, but I bet a lot of your kids at home are already doing this. Does anyone have kids that are playing Minecraft? Has anyone heard of Minecraft here? Yeah. Now, do you yell at them because they play it too much? Because you think about it, what you're doing in Minecraft is you have these little bricks of material that are scaleless, essentially, and they have material definition, right? You can have hard, rigid materials, you can have fluid materials, you can have fire, you can have rocks. I was actually playing with my nephews and nieces a few months ago, and we're building our own environment. It's a collaborative build environment. You can actually see the other people running around stacking bricks up. There's millions and millions of worlds and environments and products that have already been designed in the Minecraft world. So I say, let your kids play. That represents the future generation that gets all this. You know, it's not a change for them. This is just something that they've been doing since they started, since they grew up. So let them play. Thank you very much. Talk to you soon.
Thank you, Jordan. That was certainly a very interesting perspective, and I think everyone would agree we're just scratching the surface when it comes to additive manufacturing and the change that that's going to introduce, not just in terms of manufacturing, but in terms of how we design products to work in that world.